Hey everyone, today's mission is to take TensorFlow by the reins and teach it the art of alphabetical order. Picture this. We will feed it A, B, C and it should seamlessly predict the next letter in line, D. Now, why is this cool? Well, mastering the ABCs is like the rite of passage in the world of language models. It's like teaching a robot a roadmap that starts with the very basics. So grab your caffeinated beverage of choice because we are about to make TensorFlow dance to the rhythm of alphabets. But before we get into the technical details, we need our tools. We are importing three key packages: TensorFlow for the heavy lifting, NumPy for numerical operations, and a dash of randomness with the random module. Now let's have a look at what each of these packages do. TensorFlow, our powerhouse for machine learning, NumPy the numerical wizard, and random is very obvious. First off, we are generating our own alphabetic sequence. Take a look at this array. Now let's create some training data. We are generating sequences of 3 letters and their corresponding next letter indices. Simple, right? If you are not able to understand the loop correctly, let me help. Let's dissect this loop. It runs 500 times to create 500 examples. Here's the breakdown. Number 1. Random selection of starting index R. R is the randomly chosen number for the starting point of 3-letter sequence, creating the sequence T. A random 3-letter sequence is created using list comprehension. It starts from the randomly chosen index R and includes the next 2 letters. The generated sequence T is appended to the list set X, which holds input sequences. The index of the next letter in the alphabet set after the sequence is the target output, which is appended to set Y. Basically, what this means is we want to create sequence of 3 alphabets A, B, C, and we want to make D its prediction. Next step, we are using TensorFlow's text vectorization to convert our letter sequences into numerical vectors. It's like turning our letters into a language that model can understand. We are adapting our text vectorization layer to all the alphabets in the alphabetic set. For a better understanding of text vectorization layer, I have written this part of the code. It is not actually included in the project. In the first line of the code, I have defined an example set. In the second part, I have tried to adapt the text onto the text vectorization layer. In the last part of the code, I have printed the output from the text vectorization layer. As you can see that the output is 3 and 2, while the inputs were some text. Now, let's see our model architecture. We are using an embedding layer to transform our letter indices into dense vector, then flattening and adding some dense layer for complexity. If this is your very first model, you might not understand all of it, but after you've done some projects, you will get a hand of it. In the first line of code in inputs, you will see that the shape of input is 3, which means that the input sequence will contain 3 alphabets or numbers. For this particular model, we are using Adam Optimizer. Loss is mean squared error and matrices is also mean squared error. Now that we have configured our model, let's train it. The following code is used for the training of our model. Let's dissect the code into parts. First parameter inputted is the input data. Second parameter is the target data. Third is the batch size. Batch size is the number of samples our model processes at once, and epochs represent the number of time our model will see the entire dataset during training. For this particular training, we have set the batch size to 1 and epochs to 100. Now let's talk about callbacks parameter. Here we are using early stopping. If the validation loss doesn't improve for a certain number of epochs, patience is 5, it stops training early and restores the best weights. Lastly, we are splitting our data into parts. For validation, validation split is 0.2 for this particular training, which means 20% of training data is set aside for validation, helping us monitor how well a model generalizes to unseen data. As you can see, the loss after 3 epochs is less than 1. That the early stopping callback stops the training when the validation MSE isn't going any further down.